In this video, I would like to discuss a topic from Section 6.4 that is important in computer science. What I've written here are two sentences, and just so that we can talk about them in some way, let's call the first sentence Sentence A, and the second sentence Sentence B. Sentence A says the sentence below, referring to Sentence B, is true. And Sentence B says the sentence above, referring to Sentence A, is false. So now, my question for you is Sentence A true? Well, let's do something. Let's assume Sentence A is indeed true. What would that lead you then to understand? B is true. But if B is true, that implies A is false. Well, now we have A is both true and false. This is a contradiction. So A is not true. Well, I guess that might lead us to believe then that A is false. If we then assume A is false, then what do we know? B is false. If we conclude B is false, that's telling us that A is true. This is a contradiction. Because A cannot be both true and false. So we see A is not false. Wait a minute. We've just figured out that A is not true and it's not false. How does that fit in with the whole discussion we had back in the first chapter? If you think about when we defined things at the very beginning, well, the first night of this class, we didn't define true, we didn't define false, and we didn't define sentence. But we did define a statement. A statement is a sentence that is either true or false. So you notice, Sentence A can't be a statement. It is something that is neither true nor false. It is what is sometimes known as a paradox. And this is one form of a paradox that was discussed by the mathematician Bertrand Russell. He's discussed on page 378. He did this paradox in a slightly different way. Here's a way we can think of Russell's paradox the way he did it. First of all, most sets are not elements of themselves. For instance, the set of all integers is not an integer, and the set of all horses is not a horse. But how about the set of all abstract ideas? Well, that is an abstract idea, so that is an element of itself. So that's kind of an unusual set. Well, here I have written a set that says this S is all of the sets where A is a set and A is not an element of itself. Now, the question is this set an element of itself? Well, if you tackle this problem, you end up getting a paradox just like what we had up here with these two sentences. Either way you do things, you get a contradiction. So you cannot see that S is an element of S, and you cannot see that S is not an element of S. Russell explained this to lay folks who were not mathematicians by doing what he called the barber problem. The barber problem is something where you have a town in which there is only one barber, and the barber shaves everyone who does not shave themselves. Now the question is, who shaves the barber? Well, if you say the barber shaves himself, you get a contradiction. If you say the barber doesn't shave himself, you get a contradiction. This is kind of an interesting problem because it makes it so that we can have things that don't fit in with that whole scheme that we did in chapters 2 and chapters 3. Well, what does this have to do with computer science? Well, it fits in with something that is called the halting problem. The halting problem is a technique for figuring out whether an algorithm could ever possibly work. And you can read about the halting problem on page 379 through the end of the chapter on page 380. But let me explain this, though, a slightly different way. I think you guys should probably know what a compiler is. A compiler is something that is able to take a high-level language that's written in, say, C or Pascal or Java, and it compiles it or transforms it into something that the machine can understand. It puts it into machine language. Well, compilers nowadays have gotten to be very sophisticated. They're able to certainly offer up debugging things and give you errors. Sometimes they can even optimize code. They can help you find problems with your code. Well, suppose you're in a business like my business where we actually have a compiler for a specialized language, and you guys are going to learn about compilers if you ever take compiler theory, and you'll have to write one in a computer science class where you deal with how compilers work. Suppose you wanted to make a compiler that's smart enough that it's going to find an infinite loop in your code. Suppose your boss asks you to make the compiler find any infinite loops. Well, that becomes a problem. And in everyday language, you can talk about this way. The only way that a compiler is going to detect an infinite loop is to go into an infinite loop, and if it goes into an infinite loop, it can't get out. This is one of those interesting things where a human can look at code and detect that there's an infinite loop, but you can't write code to figure out if the code has an infinite loop. So the interesting thing about this is that what I find interesting about this whole thing about being able to figure out the limits of compilers is it was first done by Alan Turing, famous name in computer science, and there was a 2014 movie called The Imitation Game about him during World War II, because he worked with some of the primitive computing of that era. Turing was able to prove, basically, that a compiler could never detect an infinite loop. And he proved this mathematically back in the 1930s, which I think is really kind of interesting when you realize that there weren't any compilers then. And it was all a mind experiment mathematically. Of course, he did it with a mathematical proof. But it is interesting to say, well, there will be some things called compilers, and they won't be able to do this. This whole area of dealing with paradoxes can be very, very interesting. You might want to read some of this section here in your text. It also discusses Gödel. And one of the things Gödel looked at was that in any sufficiently complex area of mathematics, there would be some items that would be true that you cannot prove to be true. And he proved that. If this kind of thing is interesting to you, I suggest a book that's out there that might be interesting for you called Gödel, Escher, Bach. It was written by one of the guys who did the mathematical column in Scientific American. It's a big, thick book, not light reading, but it can be a fun book for a mathematician. I think what we've done over in these videos should help you with all the problems on Homework 4 that are associated with Chapter 6. At the end of that section, of that homework, there are some problems dealing with relations, and we'll cover those when we take a look at the next two chapters.